Of section 1.6 where we learn about absolute value functions. I'm assuming you already know a little something about what an absolute value is, like that you know, for example, that the absolute value of 5 is 5. Sorry, let me try that again. The absolute value of negative 5 is 5, whereas the absolute value of 5 is positive 5. But something to be a little bit careful of, it's not true that, maybe I'll write this in red to emphasize that it's wrong. I don't know why red would mean wrong. That the absolute value of negative x is just equal to x. This is not true. I don't even like writing something that's not true. To show that this is not true, maybe suppose that x equals negative 1, for example. Plug that in here. Prove to yourself that this is not true. So maybe that little example shows that absolute values are a little, you thought you knew everything about it, but it's a little bit more subtle than maybe you thought. When you end up solving equations and inequalities, when you have variables that have absolute values associated with them, you gotta be a little bit careful. You can't just get rid of the negative in some sense. So what that kind of does is it necessitates having a definition for absolute value. Your book will tell you that the absolute value of x could be defined as a piecewise function. It's just equal to x. The absolute value symbols don't do a damn thing if x is greater than or equal to 0. However, if what's inside the absolute value symbols, like a negative 5 up here, is a negative number, if it's less than 0, then what the absolute value symbols do, what they did right here, is they changed the sign of what was inside here. They changed it from negative 5 to positive 5. Mathematically, we could say it multiplied it by negative 1. It took this negative 5 and said, really, we want the negative of negative 5 to make this thing positive. That's one definition for the absolute value sign. I think it's kind of another way to do it. Maybe this isn't very instructive. I don't know that you'll be using this a whole lot, but I just think it's kind of clever, is that the absolute value of x you can also think of as just the square root of x squared. As you square something, that kind of gets rid of the negative part of it, but it messes it all up. Now it's squared, but the square root takes care of that. It turns out this is also true. I think this is a little bit more instructive, but I just think it's kind of clever, so I wrote it here. Probably more important than either of these definitions is for you to have this intuitive idea that absolute value gives maybe the distance from 0. So picture a number line. You got negative 5 way the hell out here and positive 5 out here. And whether you're talking about the distance negative 5 is to 0 or you're talking about the distance 5 is from 0, the answer is 5. So you can think about the absolute value as the thing that a machine that takes in your position on the number line and gives out how far you are from 0. Distance is something that's always positive. Anyways, let's see some examples here. The graph of the absolute value. That might not seem like something that deserves any time because we learned in section 1.1 that the absolute value of x, if I say f of x equals the absolute value of x, that was one of my toolkit functions. And the graph looks something like this. Looks exactly like this up and to the point, except for if you account for the fact that I can't draw very well on a computer. It's this V-shaped graph. It looks like this. And note that this graph fits this piecewise function. If you know anything about graphing linear equations, you know what the graph of f of x equals x looks like. It was a toolkit function. But negative x, it turns out, looks like this. And we'll talk about why that's true. If y equals mx plus b means anything to you, you might be able to understand that already. So what we're saying is the graph looks like this toolkit function, this guy, whenever my x value is greater than or equal to 0, so on the right side of the graph, but it looks like this when my x value is less than or equal to 0. Anyways, this is the graph of f of x equals x. Nothing new here. This was introduced in a previous section. What is new is, actually, I guess this isn't even new either. Let me give you some sort of, how should I do this? Let's go do the same one I did in the other video. At least I think this is the same one. This is a mess. I claim you know how to graph this thing. I claim this isn't new. Because really, it's just taking this starting spot and applying a bunch of function transformations, which is something you learned in the previous section. This might not immediately look like function transformations, but if you write it as negative x plus 3, maybe now you can view it as function transformations. You have two vertical transformations, this 2 right here, and this negative 1 right here. And if you just apply those to your graph, I'm going to take all the y coordinates and multiply them by 2 and then subtract 1. So 0 times 2 is 0, minus 1 brings me here. 1 times 2 is 2, minus 1 brings me here. If you do this for a whole bunch of points, you'll end up with a graph that looks something like this. Try to be somewhat accurate. But that's not your answer. That's just what you'd get if you applied the vertical transformations. For your answer, you'll want to apply the horizontal transformations as well. So you got this negative here and this positive 3 here. And what this tells you is you subtract 3 from all of the x coordinates. And this tells you divide the x coordinates by -1. And the order you apply these is you do this one first and then this one for some strange reason that I talked about a lot more in 1.5. So let's go ahead and do that. This point has an x coordinate of 0. If I subtract 3 from it, it moves it over to -3. If I divide it by -1, it moves it over to here to +3. This x coordinate right here is at -1. Subtract 3 from it, it's at -4. Divided by -1, it's at +4. You do that for all of the points, and you'll end up with a graph that looks something like this in green here. And this thing in green is my graph of g of x. So really, I mean, I guess you could think this is just review, but since 1.6 was, or 1.5 was such a challenging section, maybe it's instructive to do another example here where I have 4 different transformations. This is about as hard as you can get from 1.5, coming up with this graph right here. But now that I have this graph, I can use it. So I'm going to copy it over here as best I can. And I'm going to use this to illustrate the last 2 things I want to talk about in this video. So I've talked about the definition, we've graphed absolute values and even transformations of it. Solving absolute value equations. Maybe I ask you the question, where does, sure, 2 times the absolute value of 3 minus x minus 1 equal 3? Maybe I ask you that question. What you might note when I ask you this question is what I wrote on the left-hand side of the equation is exactly this function right here. So really what I'm asking you is when is this function equal to 3? In other words, when will the output for this function be 3? You can get that right off the graph because the output for the function is graphed on the y-axis. So you can say, oh, it's 3 right here and 3 right here. Looks like it's 3 when I put a 1 in and it's 3 when I put a 5 in. My answers should be 1 and 5. But let's confirm that algebraically. Maybe you don't have the graph or you don't want to graph this thing, or the point is not right on here for whatever reason. Maybe you don't want to rely on your graph. How do you solve this? Well, it turns out that you can solve it a lot like the absolute value symbols weren't there. You could add 1 to both sides of the equation. You could divide both sides of the equation by 2 and get to here. But at this stage, you got to be careful because you have these absolute value symbols here and you don't know how to deal with them. The way you deal with them is you're going to take your one equation and break it up into 2 different equations. You're going to think about what the absolute value symbols mean. How could I make this a true statement right here? The absolute value of something equals 2. You don't know what that something is because there's a variable in here. But just suppose for a minute that that thing inside the absolute value symbols right here is equal. There's some value of x that makes this thing equal to, I don't know, -5. The absolute value of -5 does not equal 2. So that would not be a solution. So I do not want to write an equation to figure that out. However, what if you could think about something that would make what's inside the absolute value symbols here equal to +2? What if you could find something that would make the 3 minus x, the thing on the inside, equal to 2? Can you see how that would give a solution to this? Because if what's in here is 2, the absolute value of 2 equals 2, I get a true statement. But that's not the only solution. That thing inside the absolute value symbols could also be equal to -2. What's inside here is -2. The absolute value of -2 is 2. That would give me a true statement also. People like to jump from this line to this line. They just kind of memorize that you drop the inequalities and make a plus or minus on the other side. Be really careful there. There's some examples where you can screw yourself up doing that. So really think about why you go from this line to this line. That's my advice anyways. Then solve these 2 equations. Maybe I'll add the x over to this side and I'll subtract 2 from both sides and get x equals 1. I add the x over here and add 2 to both sides, I get x equals 5. And note, those are the exact 2 solutions I got right here. What I just did is I solved an absolute value equation. If you don't want to think about this step, if I lost you splitting this up into 2 different steps, you don't have to think about it. You can always just drop the absolute value symbols and make the other side plus or minus. If I'll let you do that, I being mathematics, will let you do that as long as you promise you always check your answers. Because if you just do that mindlessly, it's not that I'm afraid that you'll make a mistake. It's that sometimes that will lead you to answers that are not actually solutions. So if you want to do that mindlessly, that's fine. Just remember that anytime you have an absolute value equation, you want to check your answers. You want to take this solution and plug it into the original and make sure that it works. If you don't want to check your answers, then think about this step and make sure you only write things here that would be solutions to this right here. Last thing I want to do is solve an absolute value inequality. So what if I asked you, when does 2 times the absolute value of 3 minus x minus 1, when is that thing, I don't know, greater than 0? When is this true? Well, there's a couple ways you could do this. You could do this with the graph. You could say this thing on the left-hand side here is the output. When is the output greater than 0? Well, it looks like it's greater than 0 all throughout here. Wait, greater than 0? Let's make this greater than 3. I guess I could have done greater than 0, but I want to be able to reuse this work. When is it greater than 3? Well, the output is greater than 3 all in here and all in there. So it looks like my answer is everything when x is greater than 5 and when x is less than 1. And I probably don't want to include 1 and 5 themselves because at those points the height is exactly 3 and I want the height to be greater than 3. From the graph, it appears that the solution is everything from negative infinity up to 3, up to 1, union everything from 5 up to infinity. Right, this interval and this interval. That appears to be the solution. Maybe you don't have the graph or maybe you don't trust your graph. Be nice if you can come up with that algebraically. That's what I'm going to show you how to do before I end this video. The way you solve absolute value inequalities, how to do this, is to refer to this. Don't worry about these until you have this third thing here down. Because the very first step in solving an absolute value inequality is to change it into an absolute value equality. Change it from this to this and solve this. Can you solve this? You can solve this. We just did that over here. I picked it so the numbers will work out the exact same. Do a bunch of steps and you'll end up with x equals 1 and x equals 5. Wait, hold up, slow on. You solve this. How's that the answer to this? This is a different question. How can the answers be the exact same? They're not. I haven't found the answers to this, but the answers to this will use these solutions and this thing called a sign line. And so what you do, step 1, change it into an equality. Step 2, solve that absolute value equality like we did over here. Step 3, create a sign line. What a sign line is it's kind of like a number line. And what you put on your number line are these two solutions, so 1 and 5. And then with these two solutions, maybe you'll notice that that divides your number line up into 3 different regions. Everything to the left of 1 here, everything to the right of 5, and then everything in between the two of them. I'll call those regions 1, 2, and 3. And the way I'll figure out whether I have solutions here is by testing the regions. I'll test region 1. Wait, what do you mean test the regions? How do you test the regions? Pick any number in region 1. So any number that's less than 1 here. What number should you pick? It makes no difference. It's arbitrary. It's up to you. I'll pick x equals 0 because zeros work out nice mathematically. But you could have picked -1 or -15/12 or whatever the hell you want. I'll test x equals 0. When I say test, I mean plug it into the original equation. Is it true that 2 times the absolute value of 3 minus 0 minus 1 is greater than 3? And I'll put a little question mark here because right now I don't know if this is a true statement. Well, it turns out it is true because 3 minus 0 is just 3. Absolute value of 3 is 3. 2 times 3 is 6. 6 minus 1 is 5. And 5 is, in fact, greater than 3. So is this true? Yes, it is true. What that means is 0 is in my solution set, but furthermore, every single number in region 1 is in my solution set. That's really powerful. Now I'll test region 2. Same way, pick any number in region 2. I'm going to pick x equals, I don't know, 2. Why? Just because I got to pick something. Plug that into your original inequality and see whether it's true or not. There's a question mark there. It's not true because 3 minus 2 is 1. The absolute value of 1 is 1. 2 times 1 is 2. 2 minus 1 is 1. And 1 is less than 3. It's not greater than 3. So no, this is not true. 2 should not be in my solution set. But furthermore, every single number in region 2 should not be in my solution set. Let's test region 3. What number do you want to pick? Any number you want. Any number that's greater than 5. How about x equals, I don't know, 13. Where'd 13 come from? Just arbitrary choice. Anything you want greater than 5. Let's test if it works. 3 minus 13 in the absolute value symbol times 2 minus 1. My question is, would that give me something that's greater than 3? It would, because 3 minus 13 is negative 10, and the absolute value of negative 10 is positive 10. And 2 times 10 is 20, and 20 minus 1 is 19, and 19, in fact, is greater than 3. So this is true, therefore these are solutions. So then you go back up here, and you're like, okay, so all of region 1 are solutions, and all of region 3 are solutions. Region 1 is all of the numbers from negative infinity up to 1. I don't want to include 1 because 1 itself is not in my solution set. 1 is a point that makes the left-hand side equal to the right-hand side, but I want the left-hand side to be strictly greater than the right-hand side. So I don't want to include 1. This isn't my final answer because I also have to include region 3, which is everything from 5 up to infinity. Again, I don't want to include 5 for the same logic. Note that this right here, same thing I came up with down here. That's how you can solve absolute value inequalities. That ends the short version of this summary.